Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 2.4 entitled Average Rate of Change of a Function. And today we're going to be talking about the average rate of change as well as linear functions that have a constant rate of change. And functions are often used to model changing quantities in the real world. So that's what we're going to focus on in this section, is how we find the rate at which values of a function change as the input changes. So for our first example here, we're going to explore this concept of an average rate of change by just diving right into this example. On a long car trip, you decide to take a nap. Before you fall asleep at noon, you notice that you pass mile marker 234. You wake up at 2 p.m. and see mile marker 354. So calculate the average speed while you were sleeping. So as you read through that, if you need to read through it a few more times, go ahead. But as you read through it, hopefully it seems familiar. Hopefully the formula that we're going to be using comes to mind, and that is distance equals rate times time. You have a certain distance that you've gone that we can calculate with our mile markers. We're finding our average speed, so that's going to be the rate. We know the time that you fell asleep and when you woke up, so we can calculate the time that you traveled between those mile markers. So if we're trying to find the average speed, that means we have to find r. So I'm going to solve this equation for r. So that would be distance over time. And the distance is the distance between our mile markers, 354 minus 234. And the time, let's see, you fell asleep at noon, and then you woke up at 2 o'clock. So that's going to be 2 hours. You could think of it like a subtraction problem. You could think of it in like military time. 1,400 hours minus 1,200 hours is 2, okay, or 200, but we really just want 2 hours there, okay? So when we subtract, we're going to get 120 for our miles, and 2 is our time. So our average rate is going to be 60 miles per hour. So that was your average speed. Now remember, that's average. It doesn't mean that you were going exactly 60 that entire 2 hours. It's not a constant speed, it's an average speed. And so this is a graph that's similar to what we were just talking about. They want us to calculate the average speed for the following intervals. Okay, so this, if we look at our graph first before we start diving into what they need us to do, here across the bottom of our graph we have our time. So we have from 0 hours to 4 hours. And then on our y-axis we have our speed, or our miles that we've gone, our distance. And you can see that this isn't a constant line. It's not a constant function or a straight line. It's got this curve in it. So that means we start off slow and then we kind of increase gradually as time goes by as we get to our distance by the end of our trip. Okay, so they want us to calculate the average speed. So again, we would need our distance over time. We're finding our speed or our rate. That would be our distance over our time. So we're using that same concept that we had before. And for the entire trip, they want us to find the average speed for the entire trip for part A. So our entire distance, okay, we're assuming that the trip is going to end here at this last point. Okay, so our total distance was 200 minus 0, and our total time that it took was 4 minus 0. So I have room on the next slide for this work. So we've got 200, or 200 minus 0, and our total time was 4, or 4 minus 0. So that's 200 over 4. So that's going to be 50 miles per hour. Now again, that's your average. Okay, the graph wasn't a perfectly straight line that showed 50, 50, 50, 50, 50 going up 50 miles for every hour. Okay, the graph doesn't show that. Okay, so that's an average. Okay, for part B, they want us to find the average speed for just the first hour. So for that first hour, our distance, it looks like, after this data point, it looks like we were at about maybe 50 miles. And that's our first hour there. So you could think of it as 50 or 50 minus 0, and then 1 or 1 minus 0. So that's 50 over 1. So again, that's 50 miles per hour. Again, that's our average. That's not a constant. And if you look at the graph, it curves. It's not a perfectly straight line. Okay, so again, that's our average rate of change. From hour 2 to hour 4, okay, so hour 2 is right here. Hour 2 looks to be maybe about 75. And hour 4, that's where our trip ended, so that's 200. Okay, so we went from 75 to 200 miles, and it took us 2 hours to do that. So we went a total of 125 miles in 2 hours. So that is actually 62.5 miles per hour. So in that amount of time, from the 2 hours to the 4 hours, our average speed was a little bit faster, at least faster than the first hour and the average for the entire trip. All right, and then part D says that they want us to find the average speed for hours 3 to 4. So at hour 3, looks like we're at maybe 125 for our distance. And then to 4 again, we're going to be at 200. So we're going to take 200 minus the 125 over 4 minus 3. So that means we went a total of 75 miles in that 1 hour, so 75 miles per hour. So in that last part of the trip, we really speed up. And that you can see in the graph. We're starting off slow in the beginning, getting a little faster in the middle of the trip, and then really speeding up at the end of the trip. And that's what the graph does. It starts off slow, speeds up a little bit, and then really starts to speed up. So overall, the average rate of change is accounting for all of those fast moments and slower moments. You're totaling it all up and averaging it out. And we really need to take a look at the formula that we've been using. And it's very similar to slope. We were dealing with the change in our y-axis and the change in our x-axis. But the function that we're going to be using is right here, or the formula we're going to be using. And it has function notation in it. So you take f of b, and b is kind of like your second location on the graph, or your second piece of information. And then you're going to subtract f of a, so that's your first location, or your first piece of information. And what you want the values that you substitute into the function and then get out of the function. So f of b is what you get out after you've put b into the function. F of a is what you get out after you've put a into your function. So you're taking the values of the function and then you're dividing them by b minus a, the actual input values that you put in. So it's kind of like your output values over your input values. So let's see if we can use that concept, that formula, to take a look at example 1 here. Remember, this is example 1 in the book. I know this really is the third example we've done. This is example 1 from the book, though, so if you want to follow along there, you can. And here it says for the function f of x equals x minus 3 squared, whose graph is shown, find the average rate of change between the following points. So in part A, we have x equals 1 and x equals 3. So that x equals 1, we want to think of that as our A value, and the x equals 3 is like our B value from that formula that we were just using. So we have f of A, oh, I'm sorry, f of B minus f of A all over B minus A. So when we put 3 into the function down here, the y, that's our x value. When we put 1 in on the x value, our y value that we get out is 0. And then when we put 1 into the function, x of 1, the value that we get out looks to be about 4. Okay? So we can use those values, or we could substitute the actual x's into this function that they gave us if we wanted to. So you can read the information off of the graph, or you can use the formula if you're given the formula or the function. So I'm going to do the work on the next. Oops, no I'm not. I thought I had an extra slide in there. Okay, I guess I don't. Then for part A here, we're going to have f of 3. Let me make a little room here. Let me erase that. Okay, so for part A, I'll do my work down here. We're going to have f of 3 minus f of 1 all over 3 minus 1. Now f of 3, if you want to substitute it into the equation, we could. We'd have 3 minus 3 squared, and then 1 minus 3 squared all over 3 minus 1 still. All right, now 3 minus 3 is 0, and 0 squared is 0. That's the value that we got out by looking at the graph. When we said if you put 3 into the function, the y value you get out is 0. So that makes sense. And then 1 minus 3, that's negative 2, squared is 4. So we have minus 4. It's minus because there's a minus in the formula there. Okay. Again, that's the value that we got out. We said when you put 1 into the function, it looks like it's about 4 here for the value that you get out. And then 3 minus 1 is going to be 2. So my value then for my average rate of change is going to be negative 2. And that's what these little dashed lines are showing here. So this little dashed line goes from 1 to 3, and notice that that part of the parabola is going down. So it makes sense that our average rate of change should be negative, because that little dashed blue line is going down, has a negative slope. Whoops. And then we're going to try that again for part B. So here we have f of 7 minus f of 4. So we're trying to find the average rate of change between x equals 4 and x equals 7. And then in the denominator, we want to do 7 minus 4. Now let's take a look at our graph here. Let's see if we can read these values off the graph. F of 7, so if I put 7 into the graph, the value I get out is all the way up at the top. If I'm reading it right, it looks like it's 16. Let's do our substitution here just to double check. We'd have 7 minus 3, which is 4, and then 4 squared will be 16. Okay. And then if I put 4 in, it looks like that gets me about 1. Looks like it's 1 unit up. Let's see. So I would have 4 minus 3 is 1. Squared is going to be 1. Okay. Over 7 minus 4. So if the graph is a little difficult to read, if it's hard to see where exactly those data points are lining up on the axes, the safe bet is to substitute them into the formula or the function if they give it to you. So we'll have 16 minus 1 over 3. So that's going to be 15 over 3, so that's 5. And again, that's what this blue line on the graph is representing, this dashed blue line. And it's increasing. It looks like it's going up about 5 and over 1, up 5 and over 1. Okay? So this formula for the average rate of change is very similar to slope, except you need those values for the function over the values that you're substituting in. So you have your substitution into your function, and that really gives you your range values, if you want to think of it like that. And then you're dividing by the values that you were substituting in, those domain values. Now, linear functions can also have a constant rate, and that's what you're more familiar with in terms of slope, where you have y equals mx plus b, or f of x equals mx plus b. So in our next example, we're going to find the average rate of change for a certain linear function. So anytime you have a linear function and your slope is constant, or your rate of change is constant, that's your slope. Okay, so in example 4 here, they want us to find the average rate of change of this function between the following points. The function they gave us was f of x equals 3x minus 5. And the way that they have this expressed here, this let f of x equal 3x minus 5, that's just a more advanced way that mathematicians communicate. They always say, let something equal something. So get used to being familiar with that expression. You're going to see it in calculus and more advanced levels of math as well. Okay, so for part A, I think I have an extra slide here on the next slide to do our work. Okay, so we're going to find the average rate of change, which should be constant, between x equals 1 and x equals 0. So I don't have a graph to look at here. I don't have a graph to read the information from, so I am going to have to substitute those values into my actual function. So I have 3x minus 5 is my function. 3x minus 5. Okay, so let's substitute in f of 1 minus f of 0. And again, this is that rate of change formula that we're using. So f of 1, I'm going to substitute that into the function, 3 times 1 minus 5. I'm going to figure out what that value is, and then I'm going to subtract 3 times 0 minus 5 over 1 minus 0. Okay, so 3 times 1 is 3, minus 5 is going to be a negative 2. 3 times 0 is 0, minus 5 is a negative 5, so I have a minus and negative 5, so that's plus 5 over 1. So that gives me 3. Okay, so let's try that again with 2 other different points. I have x equals 7 and x equals 3. So I'm going to do f of 7 minus f of 3 over 7 minus 3. So now I have to figure out what those range values are for f of 7. So I would have 3 times 7 minus 5, and then 3 times 3 minus 5. Again, I'm substituting 7 and 3 into that original function that they gave us, which is written up here at the top of the slide. And then 7 minus 3 is still my denominator. So 3 times 7, that's 21, minus 5 is going to be 16. 3 times 3 is 9, minus 5 is going to be 4. And 7 minus 3 is 4. So 16 minus 4 divided by 4, that's going to get us 3. Huh. Now remember, we had a follow-up question there. After we do A, B, and C, we want to make some kind of a conclusion. So already we can maybe form a temporary or a hypothesis to our conclusion. We could say that, hey, my rates are the same. And when your rates are the same for any part of your function, That means that it's a constant function. So let's try part C. Now part C is going to kind of prove our hypothesis because these aren't actual values. These are just arbitrary points. And this is where it gets a little tricky. I'm going to put a star by this one, but this is the level that you need to be able to work at. You need to be able to substitute in variables into a function and simplify them. So I'm going to have f of a plus h minus f of a all over a plus h minus a. Now sometimes when students look at this expression, they say, oh, I have an f of a, and this is an a plus h, so I'm going to distribute that f, so then I'll have f of a plus f of h, and then they subtract the f of a's. Doesn't really work that way, okay? What this notation means is that we have to put a plus h into that function that they gave us. So instead of 3 times x, I'm going to have 3 times a plus h minus 5. And then I'm going to subtract f of a. So that means I'm going to have 3 times a minus 5. Now in the denominator here, it's just a plus h minus a. So there I can subtract the a's off. They'll cancel each other out. But in my numerator here, let's do a little more simplification. I'm going to have to distribute this 3 to the a and to the h. So I'll have 3a plus 3h minus 5. And then in my second set of parentheses, I just have the 3 times a minus the 5. I'm going to subtract both of those. So I'm going to do minus 3a and then minus a negative 5. That's going to be plus 5. And all I'm really doing there is I'm distributing and combining my like terms. So that's not a new concept that we're suddenly doing there. And this will be all over, if I subtract my a's in the denominator, this will all be over h. Now in my numerator, I'm not quite done. I can combine some like terms here, or cancel some stuff out. I have a 3a and a minus 3a. I have a negative 5 and a plus 5. So all I'm left with is the 3h over h. And that actually reduces all the way down to 3. So for each of these average rate of change formulas that I used, I got the exact same number, 333. So my conclusion here is that the average rate of change is always 3. So that means that it's a constant function, or that it has that value of 3 is it's kind of like the slope. Okay, and what really proved that was working with part C here, these arbitrary points that we substituted in. So there's your set of homework problems to practice these concepts. Definitely show all your work. Use that function formula. Get really used to using that. Remember, basically it's the range values divided by your domain values after you subtract them. So it's the difference of the range and the difference of the domain. And if you have any questions, come on in and see me before school.